So just with that bit of housekeeping, it is now my pleasure to introduce our first keynote speaker, Professor Chris Hankin from Imperial College London in the UK. I have had the pleasure of knowing Chris for many years. He was until very recently first the founding director and then co-director of the Institute for Security Science and Technology. I've also had the pleasure, also myself and Peter, in working with Chris in his role as a director of the UK Research Institute on Trustworthy Interconnected Cyber-Physical Systems, where he has been leading the development of a community of researchers as well as practitioners working on all sorts of issues relating to cybersecurity of cyber-physical systems and environments. His own research in this area is focused on cybersecurity, data analytics, and theoretical approaches in this area, and how to provide better decision support to defend against cyber attacks in all sorts of systems, but also critical infrastructure systems. We are delighted that Chris has agreed to be one of the keynote speakers. Chris, it is over to you now. Please don't forget to pin your video as you start. You have the usual kind of 45 to 50 minutes. If you can keep to that, that leaves us enough room for questions and discussions at the end. So over to you, Chris. Thank you.
Thank you very much, Evasion, and thank you, Evasion and Peter, for inviting me to give this keynote talk. I'm going to try and share my screen now, and hopefully you'll see it in a few minutes. Good. I've pinned your video, Evasion, assuming that you're actually chairing the session. I had thought Peter was chairing this session, but let me know if I'm wrong. Can you hear me, and can you see the screen? Thank you.
Yes, we can. Thank you.
Okay, well, thank you for that introduction. As Evasion said, I was until very recently co-director of something called the Institute for Security Science and Technology at Imperial College London. The institute was set up actually in 2008, so I wasn't its founding director. I took over about 6 months after it had been created, and it was set up actually to interact with governments and other stakeholders on all matters relating to security, to try to identify how the science and technology being developed at Imperial might help with solving various challenges in the security field. In 2012, alongside Lancaster and Bristol and 3 other universities, we were recognised as some of the UK's first academic centres of cybersecurity, centres of excellence in cybersecurity research. As Evasion has mentioned, I'm director of RITICS, which actually is the Research Institute in Trustworthy Interconnected Cyber-Physical Systems, which is partially why I chose that title for this talk. And I'll say a bit more about RITICS and its history in the next few slides. In fact, what I'm intending to do is, first of all, put my slides into display mode. So what I'm intending to do is talk about the context of this talk and the work that I've done, which is primarily RITICS and an associated project called CHIOS. I'll talk, there's a scientific content to my talk, which is some of the contributions that we've made to cybersecurity for critical infrastructure systems, focusing really on fairly recent work over the last couple of years. And then before I close, I'll talk about the broader network that constitutes the RITICS community. So that's my plan. So RITICS has really existed in two phases. The first phase, actually, RITICS was an acronym which stood for something slightly different from the title of this talk. It was actually the Research Institute in Trustworthy Industrial Control Systems. The focus in that first phase from 2014 through till 2018 was intended to be very much on industrial control systems rather than the more general cyber-physical systems that we concentrate on today. Indeed, when I tell you a little more about the projects involved, you'll see that whilst there was a concentration on industrial control systems, critical infrastructure has featured throughout our life since 2014. I may refer to the name of this conference during my talk. I'm afraid I'm on Phil's side there. I call it CRITIS. I noticed that Peter also called it CRITIS, so I'm afraid, Evasion, you're in a minority calling it CRITIS. I think even Bernhard called it CRITIS. So if I do mention the conference, I'm afraid that will be the name that I'll be using. Sorry, that's just an aside. But RITICS, when it was set up, was really set up in conjunction with something called the Centre for the Protection of National Infrastructure here in the UK, CPNI. And we looked at the industrial control system space at that time and identified three key problems that we wanted to concentrate on during that first phase of RITICS. And the questions here are here on this slide. The first was really about understanding the physical effect of cyber threat to these systems. So it's about harm. We recognized that cyber attacks on critical infrastructure weren't quite the same as cyber attacks on enterprise systems. It wasn't about stealing data. It wasn't about destroying reputations. It was about actually having a physical effect on the underlying control system, potentially anyway. Although very few examples of complete attacks on critical infrastructure, even now, have got into the public domain. The second question there is about articulating those threats as business risk. And this, of course, relates to the fact that many of these critical infrastructures, many of these industrial control systems have been around for a very long time. And when they were first created, they weren't connected to the internet. They were kind of air-gapped. The air gap has become increasingly mythical, and companies need to understand that they have to protect their control systems in just the same way as they protect their valuable data. And this is still a fight that we're fighting. Companies are beginning to realize that they need to invest in cybersecurity for their cyber-physical systems and for their industrial control systems. But it's been an uphill struggle. And Evasion and his team, and in fact, Peter and his team at City have both been in the vanguard in the UK of finding ways of articulating that risk so that companies can better understand where their investments should be and the need to invest. And then the third question was really about developing novel mitigations against the cyber threat, novel, effective and efficient interventions to protect systems. Basically, when RITICS was created in that first phase in 2014, it was project-based. It was based around 5 projects. There was a RITICS project itself, which was led by me in conjunction with a colleague of mine, Professor Deep Chana. There was a project called MUMBA, which is about multifaceted metrics for measuring security and conveying risk, and that was led by Evasion, who was at that point in time in Lancaster, now has moved much of his team and all of the activity to Bristol. There was a project called CEDRICS, which was led by Robin Bloomfield and Peter at City, which was also looking at conveying risk, but was based on a formal methods approach. So the MUMBA approach is very much an example of the sort of thing that Phil was talking about in his opening remarks, bringing a human-centered approach to looking at risk. whereas the CRITIS approach very much a formal methods approach, which was developed initially for talking about safety, and has subsequently been developed further to enable modeling of security issues. There was a project called Skeptics, which was based at the University of Birmingham and led by John Easton and Tom Chotier. That was very much focused on security of railway systems, and in particular with the rollout of the European rail traffic management system across Europe. They spent much of their time during the Skeptics project looking at security aspects of that system. And that's led to, in part, their contributions to a much larger UK-based activity called the UK Rail Research and Innovation Network, which has huge investment from the train operating companies and from the railway companies to develop a long-term research program looking at the digital railway, which RITICS is now associated with. And then finally, there was a project called Caprica, which is much closer to Phil's interests, because that's focused almost exclusively on the power grid, and in particular on the synchrophaser technologies that are used to connect renewable energy sources into the power grid. And the standards which govern how those technologies work had paid scant attention to security, and Caprica have really taken a lead in building security into those technologies for secure connection of renewable energy sources into the grid. So we had a number of results coming out of that first phase. The first was one that Eva's already referred to, which was the creation of a UK-based research community focused on the areas which CRITIS is most concerned with. And this community has grown substantially in the second phase, which I'll talk about briefly in a couple of moments. We contributed to the cybersecurity strategy adopted for the UK railway system, both through Birmingham and also through RITICS more centrally. I think it was Phil saying that models have a place, and I think Peter and I would both strongly agree that models are an important part of understanding the security of cyber-physical systems, and both City and Imperial have led in RITICS phase 1 on model building to understand better the behavior of these systems and to develop new approaches to cybersecurity for the systems. Testbeds are an essential part of this work, as Phil already mentioned, and many of the partners in RITICS had testbeds, primarily Lancaster and now Bristol have a substantial testbed suite, which you'll see more of later. The Queen's University in Belfast built a testbed of sorts for their work on the power grid. And of course, the group at Birmingham were based partly in the Railway Engineering Centre at Birmingham that have testbed facilities for experiments on railway security. We may hear later about a game, a serious game for studying security decisions called Decisions and Disruptions, which was developed by Adesi's group and has been widely used beyond the critical infrastructure sector in the UK. One of the largest police forces in the UK has used it to study security-related decisions being made by its senior officers. We developed secure implementations of various components of power distribution systems compatible with the major international standards. And we also collaborated on European work on certification of ICS components. I'm sure these slides will be shared with you afterwards. You'll also find some information about some of these things in the paper that I've contributed to the proceedings, but there are some images at the bottom which give some pointers to some of those activities. In RITICS phase 2, we've grown the community further. I think as of today, there are something like 17 universities in the UK who are part of the RITICS community, the academic community. And alongside that, there's an industrial community with between 35 and 40 participants from various, ranging from operators of critical infrastructure through vendors of equipment to critical infrastructure operators, through regulators to consultancies. We've got a broader set of questions for this second phase of RITICS, which runs through till 2023. Down the right-hand side of this image on this slide are the three questions essentially in shortened form that we had with RITICS phase 1, because not all of the questions were really answered by our work in phase 1. So there's still issues around how cyber threat translates into physical harm to systems. There's still the need to properly communicate risk and have new ways of understanding risk. There's certainly still work to be done on protecting systems, because the cyber landscape, as you well know, changes radically all the time. So new techniques for protecting and mitigating against cyber threat are necessary. And then there are three new areas which concern responding to cyber events. So this is, if you like, about resilience of such systems. There are some questions around the economics of protecting critical infrastructure systems. And then, despite the fact that there's been lots of good work done here in the UK and elsewhere in the world around those 5 other questions, there are still companies which fail to implement the best of breed approaches to protecting their systems, and we need to understand what the barriers are that prevent people from protecting their systems to the full extent, beyond budgetary limitations. In the center of this diagram, you also see that the focus of RITICS, as the name has changed, because now RITICS is not, the ICS is not industrial control systems, it's interconnected cyber physical systems. But the focus is still on looking at industrial control systems, critical national infrastructure, and then in addition, other types of cyber physical system. So we have building information management systems, for example, which are rapidly being developed in such a way that they share many of the features with CNI and ICS in terms of vulnerabilities and also in terms of opportunities for attackers to do mischief. And then there's also the industrial Internet of Things. So that's the IIoT acronym in the top left hand of that inner circle. So that's all about RITICS. Just for some background, just very briefly on KIOS. KIOS is also focused on critical infrastructure. It's a teaming partnership with the University of Cyprus. It's one of these large Horizon 2020 teaming projects. I think there's 4 or 5 of them. This one is between Imperial College London and the University of Cyprus. The teaming projects were only required to have 2 partners, and those are the 2 partners involved in this one. Full project's worth about 43 million euros and runs over 15 years. The Horizon 2020 part is a 7-year activity, and some of the work I'll talk about later is partly done by people working with me at Imperial on KIOS, the lead figure being Martin Berrer, who's a co-author of the contributed paper to the proceedings for CRITIS. This project is a collaboration between electrical engineers and computer scientists at the University of Cyprus. It's led by the Department of Electrical Engineering, and it's looking at various critical infrastructures which are important in the Cypriot context. So it's looking at water, of course, and grid, power grid, and communications. Transport's also important, but those of you who know Cyprus will know that there's no railway system and there are very few roads. So whilst transport is an issue, it's not as important to Cyprus as clean water and grid and so on. You can see the importance that was given to this teaming arrangement by the names which appear at the bottom of this slide, which I included just to emphasize that. So the opening of this teaming activity was supported by the President of the Republic of Cyprus and the Director General of Research and Innovation at the European Commission at that time, Robert Jan Smits, and also, of course, by the Rector of the University of Cyprus. So this started in 2017, and as I say, I'll say a few more about some of our scientific results from that shortly. Now, we recognize that trustworthiness, which is a word that we've used in the title of this talk, is many things, and it encompasses all of the words which appear in this slide. It's about reliability of the systems, it's about safety, it's about resilience, it's about dependability, it's about privacy, and it's about trust. It's all of those things, but we would argue that at the heart is cybersecurity, or maybe just security. And of course, given that the acronym CRITIS or CRITIS, as far as I understand it, the S stands for security, it's appropriate in this conference, and also because of my academic background and so on, that we focus on security. So I won't be saying awfully much about those other aspects, but we certainly recognize that in order to be a trustworthy system, the system has to display those other attributes as well. And I think there are a number of challenges to achieving that trustworthiness. And some of them are specifically challenges to achieving the security of the system. And the first one, I'll just refer back to that first question, which has survived through the two phases of RITICS, which is about understanding the physical harm that arises from cyber threat to these systems. And I think we're hampered there by the fact that many of the people who work in cybersecurity come from a computer science education. And indeed, I'm probably one of the first generation of UK trained computer scientists. I did my first degree in the very early 1970s. In fact, I'm an alumnus of City University, which was one of the few universities at that time teaching computer science. And at least during my computer science course, I did a lot of mathematics because there wasn't much computing to learn. And I did a lot of analog computing. So I learned quite a lot of electrical engineering, I guess, as well. And I think at that time, there was room within the syllabus to give some appreciation of physics. And I think that's something we've lost in computer science curricula over the years, because computer science has become such a big topic. So I think when we talk about cybersecurity generally, that's fine. When we talk about cybersecurity of cyber-physical systems, we've got a bit of a deficit in the computer science community with respect to understanding the physical world and the impact that cyber threat might have on the physical world. So I think that's one challenge which we need to think about going forward, because going forward, cyber-physical systems will be the majority of systems, not the minority, I would claim. If you just look at the Internet of Things as an example, think about how many devices are connected to the Internet today, and depending on who you speak to, you'll get different numbers, but there's broad agreement, I think, that it's at least 30 billion, which is fine with the world's population, with something like 5 billion people using the Internet. That's 6 devices per person. That seems reasonable, given that many of us have phones, tablets, and multiple laptops, for example. It's not an unrealistic figure. I read a report from Cisco recently which suggested 500 billion devices might be connected to the Internet by 2030. That's probably complete science fiction, but at the same time, it's maybe not far short of reality. And if there are that many devices connected to the Internet, then the majority of them are not going to be smartphones, tablets, and laptops. The world's population isn't going to grow that fast. So the majority of devices are going to be cyber-physical devices, controlling things like our fridges, our kettles, our toasters, the lights around our ponds, and the electric lights in our houses, and many other aspects of infrastructure around us. So the cyber-physical threat is going to become potentially the most important threat to our environment and to our livelihoods. Moving on, interconnectedness and interdependencies. So basically, this is about all of these devices that we've just been talking about. It is the Internet of Things. They are connected to the Internet. And there will be interdependencies which aren't explicit, but which we will need to worry about in terms of the resilience of our society. Interdependencies like the rather obvious one, for example, between the power grid and almost everything else. So if the power grid goes down, communications go down at some point afterwards, and many other aspects that we take for granted at the moment suddenly stop working. So studying those interdependencies and understanding them is going to be an important feature of having secure, trustworthy, resilient systems going forward. The digitalization process that's gone on, and particularly in control systems, as I said earlier, traditionally air-gapped maybe from the world, now increasingly the components within control systems are fully functional compute devices connected to the internet. And often there's a certain homogeneity, sorry, I can't even say the word now, homogeneity that creeps in. And if the systems are homogeneous, then that facilitates to a certain extent the spread of things like malware. A good example of that, although this wasn't the only reason that WannaCry spread so rapidly through the world, WannaCry partly spread rapidly through the world because of the predominance of unpatched Windows XP systems. The reason it hit the NHS in the UK so badly was because the NHS traditionally has been fairly cash-strapped, doesn't invest heavily in cybersecurity, and had many unpatched Windows XP systems running both their IT, but also actually embedded in medical devices and so on. So WannaCry, the worm spreading WannaCry, was readily able to infect many systems by using that homogeneity across those systems. And then increasingly as we go forward, we hear that people will rely on artificial intelligence and machine learning to cope with the data deluge that arises from this prolific growth in digital devices, amongst other things. And one of the challenges there, of course, is that at the moment, attempts to actually produce explainable AI and to understand the real semantics of machine learning algorithms and so on, lagging far behind the technical developments in that area. And I'll return to that later. This slide just shows some of the other trends which are going to be issues going forward. And some of these we're already addressing in RITICS, as I'll mention right at the end of my talk. The slide is largely plagiarized from various documents coming out of the CISA agency in the States, the Cybersecurity and Infrastructure Security Agency. It's had various names during its lifetime. It was created in around about 2009. In the top of this slide are a couple of boxes from a report which was published in 2018. On the left-hand side are enumerated a number of emerging trends, and they range from things like bring your own device, which might be somewhat surprising, but certainly in the industrial Internet of Things, I've attended presentations where vendors have actually lauded the fact that control engineers would be able to use their own smartphones and tablets to control manufacturing processes. So bring your own device will certainly come into this sphere. The use of virtual machine technologies, putting things like data historians and so on onto the same physical device as some aspects of the control system. These would normally have been physically sort of in different segments of the network, but virtual machine technologies open up the possibility of optimizing the use of hardware by using virtual techniques, all the way through to leveraging cloud services in industrial control systems. And I'll talk briefly about that later on. The attack methods, many of those are fairly standard cybersecurity attack methods, so I won't say very much about those. Just point you to the bottom of the slide. CISA and its precursors over a number of years now have collected lists of most prevalent IT and OT weaknesses. And I suppose the surprising thing, and maybe I should have put more of the history on the slide, is that these weaknesses don't change very much over the years. So if you go back over the last 5 years, you'll see pretty much the same 5 things being mentioned. In fact, before this year, before 2019, they tended to list the top 6 weaknesses. So you'll find boundary protection, principle of least functionality, identification and authentication, etc., in that list in some order over the last 5 years or so. So the messages are getting out very slowly that things have to be done in order to protect these systems. The principle of least functionality, I think, is a particularly interesting one, because this is about the fact that people increasingly are using, as I said earlier, fully functional compute devices in various components of control systems, and leaving much of the functionality for those compute devices enabled. Unnecessary functionality, which then increases the attack surface and enables attackers to potentially exploit those systems. So now I want to come to the part where I talk about some of our own contributions. So I'm going to talk about some work we've done on monitoring of cyber-physical systems, some work on measuring cyber-physical security to identify critical components, some work we've done on software diversity, and finally, briefly, some work on the use of artificial intelligence in intrusion detection and some of the issues around adversarial machine learning. So first of all, for monitoring, we have a proof of concept real-time monitoring tool called CPS-MT. This is work done partly through RITICS, largely through my involvement, but also through CHIOS, the Centre with Cyprus, but done at Imperial. And this monitoring tool was designed with a focus on providing us a mechanism to do security research. I guess one of the gold standards in this area might be the Emulytics system developed at Sandia, where basically they allow a mix of modeling with hardware in the loop to actually do security research and other research on control systems. This is our homegrown version. Basically, we use an in-memory database. We use Redis, where monitored elements can publish their status and various pieces of data. And then CPS-MT, the monitoring tool, subscribes to that Redis database so that it can read information from the monitored elements and present them using some kind of human-machine interface, a web-based interface, in fact. And we've deployed this, and I'll have a slide which just shows that in a water treatment system. So this is the general architecture. So the bottom bit is actually the CPS-MT system. You can see it's a client-server architecture. It's the server which actually subscribes to the Redis database and monitors the various devices and so on that are writing into that database, which is shown at the top, which is a mix of sensors, actuators, and other devices. And basically, after some processing in the server side, on the web browser side, on the client side, we have essentially a web browser to render the information about the things that we're monitoring. And that's mainly using a JavaScript library called D3 to actually produce various charts, examples of which we'll see in a couple of minutes. So this is the monitoring system for the water treatment plant. In fact, it's not got, in this diagram, there's actually no real hardware components. At the top, there's a Simulink-based model, which is the sort of model that control engineers might use. This is a very simplified water treatment system, which just basically has a reservoir, a valve connecting the reservoir to a tank, a pump which pumps water out of that tank through another valve into a tank from which the demand side can draw water. And then in the lower part of the diagram, there's another model of that system, which is using a system called Mini CPS, which is a modeling system for the network structure used in cyber-physical systems, which was developed at Singapore University of Technology and Design, which previously have been a partner of ours, both at Imperial and indeed also with Bristol. So the Mini CPS model models three PLCs. PLC1 is modeling the left-hand box in the top. PLC2 is controlling the valve, and PLC3 is controlling the demand tank. And basically both the Mini CPS and the Simulink simulation are able to read and write into the Redis database. We use the Mini CPS model to actually do our cybersecurity experiments. And basically the effect of, for example, man-in-the-middle attacks can then be played through in the Simulink model by changes to readings of the pump and, settings of the pumps and the valves in that side. And then CPS is on the side there, subscribing to the Redis database, enabling a web interface to monitor what's going on in these two systems. As I said earlier, our intention is, and indeed we've done some initial experiments, to replace some aspects of the Simulink modeling with actual hardware. And this is just an output which shows the tank level on the left-hand side of the previous diagram, which is being controlled by the first PLC, and the behavior of the valve, which is also being controlled by that PLC. And then the bottom one is showing a flow level through the valve, which is being controlled by PLC2. So that's the sort of thing that the monitoring tool allows us. So I'd like to move on to the second contribution, which is called Metaphorics, which is shown up at the top left-hand side there. And this is a proof of concept tool to identify critical cyber physical components in the system. And what we do here is we start by drawing a graph of dependencies in a system between devices, dependencies meaning that a device that depends on other devices is actually taking readings or some input from those other devices or processes. And one of the novelties of this approach is that we represent those dependencies using and/or graphs. So often dependency graphs seen in the literature are just and graphs. Everything depends on its precursor, a node within the graph depends on all of its precursors. We recognize the fact that with redundancy in systems, those dependencies may not be absolute. So we represent that using and/or graphs. In fact, we represent it using and/or hypergraphs because we also model some aspects of physical security in our dependencies, so that devices which might, for example, be in the same locked enclosure will appear in a hypernode, which incorporates both those elements, or all of those elements which are in the same enclosure. We translate that graph into a logical formula, a propositional formula, and we then use MaxSat solvers, in fact partially weighted MaxSat solvers, to calculate critical components. So there are weights in the hypergraph which indicate the work that an attacker might have to do to compromise a particular node. And the output from the solver gives us an indication of which are the nodes in the graph which are cheapest for the attacker to compromise, at the same time ensuring that the system can't operate any further. And as I said, we use hypergraphs to model both physical protection and the cyber aspects. So essentially, the proof of concept system takes one of these input hypergraphs in JSON format. It analyzes the graph to actually extract a logical formula, which is the formula which eventually we will try to satisfy in order to identify the critical components. Many of the solvers require that these propositional formula are in conjunctive normal form. That in itself is a computationally very hard problem, but we have an efficient transformation called the Cyton transformation, which transforms the formula into a formula that's equi-satisfiable with the original formula. We then use, in fact, parallel SAT solvers, because we discovered that different SAT solvers have different bad cases. So we use many different SAT solvers and take the first that produces a result. So we get some results, again in JSON format, and then we use D3 to actually visualize the results in graphical format. So here's the sort of very simple example. We've shown that this technique scales to very large networks. This is a very small network to fit onto a slide. Basically, it's a system which has an actuator, which we want to have continuing to operate. It's got various software agents, B and D, and some sensors. And basically, so by analysis of the industrial control system, the first step is to produce this hypergraph in the right-hand side of this slide. It's a hypergraph because there are some physical protections around the sensors A and C, around the agent B and agent D. Sensor A is in a locked cabinet inside the enclosure that it shares with sensor C. So we can have multiple levels of protection there. And then there are numbers associated with the hypernodes. And those, as I said earlier, indicate the amount of work, the amount of effort, if you like, that the attacker would have to expend in order to compromise that node. So that graph is then input into the analysis, which turns it rather trivially into, first of all, a propositional formula, and then uses the Cyton formulation to produce the CNF form. And then we use the MaxSat resolution methods to actually identify the critical components. And as output, coming out on the left-hand side labeled C, we get a set of security critical cyber-physical components. And in this case, essentially, given the and/or structure, hopefully it can be seen that the least amount of effort the attacker has to expend is to compromise both sensors A and sensors C. Also, of course, the attacker could have compromised agent B instead, which would have disabled the two AND nodes, which are shown on the hypergraph, but that would cost 5, whereas compromising sensors C and A costs 3, since it costs 2 to compromise the outer defense, and then a further 1 to compromise sensor A as well. So the critical components are A and C at a cost of 3, and that then gives some advice back to the operator of the industrial control system that that's where the first line of defense should be concentrated. So in fact, Metaphorics produces this sort of output, and after the analysis, the nodes which are the most critical are circled with the red dotted arrow, dotted lines, and the cost can be computed using S1 and S3. So that's Metaphorics, and we've used this, as I say, for very large systems. We've looked at part of a real water distribution system and identified weaknesses within that. We've also used it used essentially the same techniques to do fault tree type analysis on aviation systems to identify critical components in fly-by-wire aviation systems. So the third topic I wanted to talk about briefly is software diversity. And here I'm talking about software diversity in networks implementing control systems. And basically, because we're talking about networks, we approach software diversity essentially as a graph coloring problem. Nodes within the network can actually have multiple colors, but the objective of our software diversity work is to distribute products across the network in such a way that basically neighboring networks are as dissimilar as possible, because we believe that similarity facilitates the spread of malware in the way that I described for the distribution of the WannaCry malware. So our work uses optimization techniques again, and the outcome of the work is an optimal allocation of multiple products respecting certain constraints across a network to slow the spread of malware. So the similarity measure we use is based on looking at vulnerabilities of products using the National Vulnerability Database and CVE measures. And we compute something called the Jacquard similarity. So we take two products, we look at the number of vulnerabilities that each has, and then we look at the number of shared vulnerabilities, and we divide the number of shared vulnerabilities by the total number of vulnerabilities that each of the components has, and that gives us a measure of how similar the systems are. And you wouldn't be surprised to see, if you look at the paper which is cited in the proceedings, you'll see there's a table there which unsurprisingly shows that many Windows systems are somewhat similar, for example. But more surprisingly, you'll find that some Windows systems and some Unix-based systems are also somewhat similar. So reuse of code by different vendors has led to certain numbers of shared vulnerabilities. We focused on vulnerabilities here. It seemed a natural thing to choose when we were looking at propagation of malware. But you could use other things to measure similarity as well, or enhance our similarity measures using things like shared code base and so on as a direct measure, rather than shared vulnerabilities. So this is really, again, a piece of proof of concept work. But we have nodes which then have multiple labels on each node, which correspond to the products deployed on those nodes. And these can effectively be represented as a Markov random field. And then we use an optimization technique to get an optimal assignment of products to nodes to reduce the similarity between neighboring nodes as far as possible. And we can have constraints, so we can have the fact that maybe certain web servers are unable to run on Unix systems, for example. That can be expressed as a constraint, and then that will be used in the optimization algorithm to make sure that we don't assign that web server to that Unix-based system, for example. And then we've done some visualization using NetLogo. And again, just as I said previously with the critical components analysis, we've shown that this sort of technique scales to very large networks. So it is a practical way of actually proceeding. This is a very simple example, and I've noticed that time is running on, so I won't dwell on it, but it's a very simple network, obviously. It's just focusing on web servers and database servers allocated across a network, and it doesn't really tell us very much. It just shows a particular allocation that the algorithm might come up with. I just want to finish very briefly by talking about the AI stuff. So we've done work within the team at Imperial looking at intrusion detection and using deep learning to spot anomalous network traffic. We've then been looking at evasion attacks, where an attacker might try and circumvent the deep learning algorithm to actually mount an attack. And then very briefly, I'll talk about some of the recent work we've done on instrumenting deep networks, particularly feed-forward networks, convolutional neural networks, to defend against such adversarial attacks. So this slide is taken really components from a paper by my colleagues Chen Feng, Ting Li, and Deep Chana. I should say a lot of the software diversity work was actually done by Ting Li as well. And this is really the basic work that they started with, which was looking at a gas pipeline example from the literature, developing a novel approach to a multi-level approach to anomaly detection. The approach uses a signature-based sort of Bloom filter detector at the front end. So it builds up a set of signatures of well-formed packets in the network traffic, and then uses that filter to filter out malformed packets. So that's the first level. And then the second level, some of the attacks on this gas pipeline example are actually temporal attacks. So it's a series of packets across the network which constitute the attack. So they developed a time series anomaly detector, which uses long short-term memory networks cascaded to look at temporal sequences and then detecting anomalies by predicting the most likely next packets in a sequence and filtering out those which don't conform to that prediction. So the table in the bottom right-hand corner shows some results. The table, of course, wouldn't be there if it didn't show that the approach based on the multi-level anomaly detection presented here does somewhat better than most of the other approaches that were in the literature at the time, which was in 2017. The other approaches include Bayesian networks and support vector machines and principal component analysis combined with support vector, for example. Now, evasion attacks, you may all be familiar with what an evasion attack is, but this slide is just there to sort of illustrate the idea. This is from the image processing domain. It's a very early paper on evasion attacks from 2013. And basically, of course, what it shows on the left and right-hand side, apparently to us, is an image of an American school bus. And what the authors of the paper did was carefully craft what looks like random perturbations, but of course it was carefully crafted in the middle there, which effectively adds some noise to every pixel in the left-hand image without disturbing the image from our point of view as human observers, but from the algorithm point of view, the algorithm then looking at the perturbed image on the right-hand side identified an ostrich rather than a school bus. So this is basically adding sort of noise to an input signal to actually fool the classifier. And my colleagues again, Feng Cheng, Ting Li, and Deep Chana were the first people within our team to look at how you might use this sort of attack in industrial control systems to circumvent the kind of state estimation process that was going on in our temporal intrusion detection system. So basically an attacker is able to sit between either the sensors or and the PLCs, sensors and actuators and the PLCs to change measurements or change commands going back to actuators. And essentially their approach assumes that the attacker can sit there for a period of time, and they use a Wasserstein GAN, a generational adversarial net, to actually learn the behavior of the intrusion detection system. And then on the right-hand side, there are some tables showing that under various different attack scenarios, which I don't have time to go into in detail now, the attacker was able to achieve somewhere between 85% and 90% success rate for the gas pipeline example. And then the bottom table is actually looking at chemical doping in a water treatment plant. And again, the success rates are all around 90% for the attacker if they can sit in the system long enough and learn how the classifier is working in order to circumvent the anomaly detection. So there are many defenses one can put up to try and detect this. Because of time, I'm just very quickly going to flash this slide up because I want to move into the final bit of the talk. But this is a particular approach we've developed, which is at the moment only for feed-forward networks. It uses autoencoders and decoders to actually instrument a feed-forward network between the layers of the network by mapping the signals down into a lower dimensional space, where we're able to, with some success, identify adversarial interference with the signals. This is really work of Giulio Zizou, who's one of my PhD students, who's now actually transferring this to the industrial control system setting. So just to finish up, I think I've got about 10 minutes, so I'll talk for about 5 maybe, and then have some questions, but then I'm around between 11 and 12 for deeper conversations if people would like to have them. I'm afraid I'm sitting in a kitchen and I'm being interrupted by the ice maker on this American fridge. Maybe someone's connected to it from the internet, but I apologize for the background noise. So the RITICS program that we have now in the second phase of RITICS is a 7-part program at the moment. We've been very concerned, the UK generally has been very concerned about the rollout of the Network and Information Security Directive, which came into force in 2018 for operators of essential service in the European Union member states. The UK has adopted this regulation, and we then set up a research program to identify where operators of essential service were, the baseline, what might be barriers to them adopting the provisions of the NIS Directive, and what the impact for early adopters might be in terms of their overall business. And then there were 6 other areas that we've looked at: safety and security, autonomous systems, incident response and forensics, cyber controls, interconnected systems, and supply chain. So I don't think there's time to go into what each of those are in detail, but hopefully the words used in the titles are enough to suggest what they might be about. Just very briefly, the projects that we've run on the NIS Directive, we've had 3 projects running. None of these projects have yet finished. They're all running through till the end of March next year. So there are very few results, but we may hear some of the results from Bristol later on. Bristol was looking at sectoral differences across the operators of essential service space to understand how different sectors were responding to the requirements of the NIS Directive. And then the 2 other projects were both looking at supply chain aspects. Birmingham specifically looking at some of the hardware requirements that might be put on third-party devices being deployed in critical infrastructure. And then Glasgow looking at this baseline question for supply chain resilience. And then we've got 4 other projects running which come from the other areas on that landscape slide that I had 2 slides ago. We've got something called AIR for ICS, which is looking at how agile techniques from software engineering might actually allow a more agile approach to incident response for industrial control systems. The methodology that they're using there is by running a number of red team and blue team exercises. The red team are professional cyber hackers. The blue team are drawn from a variety of different sort of areas, but typically are trainee control engineers and more experienced people from the critical infrastructure sector. And they've looked at port security, they've looked at power distribution systems, and they've got other exercises planned. COVID-19, of course, has made that sort of work quite difficult. Then we've got Queen's University Belfast are running a project called Cosmic, looking at the safe use and secure use of cloud to support forensics and also to support industrial control systems generally. And so moving things like the data historian and so on into the cloud in a secure way. Then Glasgow are leading another project which is looking at the different training techniques that need to be used to actually train forensics people in safety-related industrial control systems. They focused on areas like civil nuclear and power. And basically they've got a small test bed and they've looked at various groups of people ranging from junior control engineers through experienced control engineers, cybersecurity people and managers, and looking at the different teaching techniques and so on that are most effective for those different sort of groups of people. And then Peter led a project looking at safe and secure systems, which was a kind of scoping project. And in fact, it may be timely to say that for all of those 6 areas that I mentioned, other than the NIS Directive, there's a new call out for RITICS, which closes at the end of next week, which still covers all of those 6 areas. So I hope the UK-based people listening to this talk might consider putting in proposals to that call. So it just remains for me to say thank you. The website for RITICS, which covers both phases, is ritics.org. My email address is c.hankin@imperial.ac.uk, and I'll be around for the rest of the morning to take any questions. Thank you.